Well, hello everyone. Thank you so much for joining in. I'm really happy that we are doing this. Welcome. This is the first stream that I have programmed, and we're going to start right now. Right now, we're going to give a presentation, a tutorial today that we have been working with Jatin for quite some time, about 2 months. We presented it 2 weeks ago in a conference in London. And yes, we're going to start right now. So let me please present Jatin. Jatin, you are online right now, being streamed. And yes, welcome. Thank you so much for joining me today again. I dragged you again into another experiment, but yes, quite a few people actually during the conference and on LinkedIn asked me about this tutorial. So since we put quite a bit of work here, we said, why not, right? Let's make the most out of it, and let's share it with as many people as possible, and to try and demystify some of the misconceptions we have about neural audio in real time for low latency. I think it's going to be a good resource once it is out there for as many people as possible. Welcome.
Hi, yeah, thanks for having me.
My pleasure, my pleasure. And well, what do you think if we shall start the presentation then? We start the presentation, we're going to present ourselves, and we'll go from there, okay? Sounds good. Fantastic. Well, then again, welcome everyone. I am really happy to present for the first time online, and for the second time this tutorial, this presentation about real-time neural audio, where we're going to talk about neural networks specifically for processing and understanding audio signals. And when we want to implement these systems for real-time use, well, we need to have some considerations about design. And of course, after we design these models to make them suitable for real-time inference, we need to execute them in a specific compute framework. It's usually not the case that we can just train these networks and drop them into a different platform and make them run. So there's a few considerations that we want to disambiguate and perhaps demystify, if you wish, about design and inference on real-time audio. So we are going to start. We're going to start right now. And what are we going to talk about in this presentation? Well, first of all, we are going to introduce the general applications on real-time neural audio. Then we're going to move into latency requirements. That is, how long do we need to wait until we have a valid result for the different types of applications of neural audio. Then we are going to try and make a comparison between continuous and non-continuous processing. That is, continuous processing is the way in which we are running the network and we are processing audio as it comes, as we receive it. We are going to talk about the differences between training a neural network for audio and then running it in real time. We're going to talk about a specific configuration for these algorithms that is called streaming, which is the configuration that allows these algorithms to be processed, to process audio as it is coming and keep on processing as we receive the audio. We're going to talk about some architectural modifications that we need to do for streaming models. And we're going to then introduce a special platform framework for real-time inference of neural nets that was designed by Jatin and a team. It is an open source project that is really cool, really interesting, and it's called RTNeural. And finally, we're going to run through a Colab notebook where we're going to train a neural network for audio and then implement it in RTNeural, and close with some final remarks. So, Jatin, if you want to present yourself very shortly.
Sure thing, yeah. So yeah, my name is Jatin. I'm a kind of freelance audio developer from Seattle. And I used to study at Karma, and then I worked for a little bit at Tesla. But for the last maybe 4 or 5 years, I've been mostly just making plugins for whatever company wants, or I've made some open source plugins under my own name as well. And just recently, I'm starting my PhD at MIT, so I'm very excited about that. And yeah, excited to keep working on neural inferencing and neural network stuff in general.
Yeah, that's absolutely fantastic. And well, I'm Franco Caspe. I'm a PhD candidate in London at C4DM and the Augmented Instrument Lab, part of both the Queen Mary University of London and Imperial College. And during my PhD, I spent right now 4 years developing low latency AI models for audio, particularly for really low latency instrumental interaction, that is, interaction with musical instruments. Besides that, before I started my PhD, I did a working experience for 3 years on real-time systems, but not particularly for audio, but for different types of video communications, defense, and computer vision. So yes, we both been working on real-time systems for quite a while. And well, let's continue then. Let's try to introduce this topic, particularly talking about applications of neural audio, trying to understand what different applications do we have and why is this important. So we could talk, before we delve into waveform and we delve into the special application that we're going to talk, we could also say that neural audio, there's a part of symbolic neural audio that exactly processes symbolic information, such as notes in a music sheet, a piano roll, or a MIDI file. The whole idea of this system is that we have different applications for neural audio, for symbolic music and symbolic audio. And one of them is transcription, for instance. So that means that from a waveform, we run a neural network, a model through this waveform and output, again, like a symbolic collection or representation of audio that can be MIDI, piano roll, or notes in a music sheet. We also have synthesis, expressive synthesis of audio. We can feed a neural model, a generator, a MIDI file, and obtain a waveform or a rendered waveform of a particular instrument. And of course, we have some other type of multimodal generation. For instance, from a text file, from a book, we can predict the notes that would accompany that particular content. So, but besides this symbolic music, we also have the waveform, which is a little bit more closer to what we are working. And waveform also admits lots of different processes for generation, for analysis, for source separation. So we can have a generator that takes a waveform as a reference and outputs can be a different waveform for an automatic accompaniment, or it can be a text file. We can have these applications for text to music that are very, very common right now, and they are in the news pretty often. Or we could have, for instance, controls of a synthesizer, and we could feed these controls to a generator and produce a waveform. We also have processes for analysis of waveforms. So we have a waveform, we process it using a neural network, and we can obtain a text description or a set of synthesizer controls that would give us back the same audio. Or we can have a fingerprint that makes kind of for automatic classification of music content. And with this fingerprint, it would be much easier to compare the content of this waveform instead of in the original sample domain. We have, of course, source separation, which is a task on which we have multiple stems mixed down into a single file, single waveform, and we separate, for instance, the bass, the drums, the guitar into the different stems. And we also have audio effects, and we're going to talk a little bit more about audio effects in this presentation. And audio effects can be from emulating a compressor to upsampling an audio signal or enhancing the audio quality of an audio signal. But the whole idea is that we have an input of a waveform and we generate an output which is also a waveform. Well, okay, so let's talk for a second about inference speed. The concept of inference is the process over which I feed this neural network an input, and the neural network gives me an output. It's called inference. We can call it also the processing of the input. We can call it also prediction, if you wish. But this process that is called inference, well, all these applications that we have require a certain speed for usability, right? We don't want usually to have an audio file, process it, and have to wait like hours until we get a result, right? So if we have, let's consider that we have processing audio, that we have a pre-existing audio in our computer in a hard disk, and if we want to process this audio, well, this idea is pretty simple. We need these models to run, at a speed acceptable over which we can actually iterate, modify the input, rinse and repeat. The idea is that, for instance, I'm trying to, process an audio signal to apply a compressor, right? A compressor that is emulated by a neural network. Well, I want to feed audio to this compressor, get a result, and if I don't like it, I may be able to change some parameters of this neural compressor in order to get a new result. So for these cases, usually the performance requirements are defined by the user patience. The same as if we are performing source separation, for instance. I don't want to wait for an hour to get the result of a source separated stem, because perhaps I want to change my song. I want to try with a different configuration, modify the gain of these outputs. So it depends on the user patience. When we have the audio already pre-existing, it depends on the user patience. And when this is the case, well, we can actually run this neural network that it has been already trained. We can run it in a CPU. We can have like some MacBooks have like an onboard neural engine, which is an accelerator. We can upload this audio file that we want, for instance, to perform stem separation to a GPU cloud, process it online, and then have the results downloaded back. And we can use all of the common neural network inference and training frameworks, which are typically run in Python, such as JAX, TensorFlow, and PyTorch. Well, Jatin, do you want to say something about real-time processing then?
Sure thing, yeah. So generally, if you're thinking about something like phone call processing or audio effect processing or things like that, you have the situation where audio is continuing to come in as time passes. You have new audio that you need to process, and you need to kind of process it as it's coming in and spit it back out as it's coming in. And so because of that, you have a bit of a kind of a cap on how much latency and jitter is acceptable. And so if you're in a situation where you're playing music, like you're playing a musical instrument like guitar, or you're singing or drums or something like that, then in order to have kind of that tight feedback loop between what you're playing and what you're hearing, you need pretty low latency like very low jitter. So I think kind of the rule of thumb is that you want your latency under 10 milliseconds. And even that depends a little bit on like the style and the instrument that you're playing. So if you're playing like ambient music, maybe you can get away with a little more latency. If you're playing if you're a drummer or you're playing some very percussive and rhythmic music, then you probably want the latency a bit lower. There's also some other applications you might want to use. So like, for example, if you're doing like a communications thing, then maybe you can get away with a bit more. So, if you're doing like echo suppression or some kind of voice enhancement, that kind of thing, you're kind of in like a conversational way, you're kind of talking and then the other person hears you and they respond. And if there's, a few more milliseconds of latency in that exchange, it's not such a bad thing. And it doesn't really disrupt the flow too much. Once it gets longer than maybe 150, 200 milliseconds, then you'd probably notice it and it'll disrupt your flow a little bit. But you have a bit more wiggle room than in the music case. And so in order to achieve these types of latency and jitter requirements, we usually see people implement their inferencing process with some kind of specialized framework. Usually this will be in some lower level language where you have more control over kind of things that you need to do to make your code run in a real-time way, which we'll get back to later. So you'll see people writing code in C++ and Rust and things like that. And you'll see some inferencing engines like TensorFlow Lite or RTNeural. And again, we'll talk about this a little more later on.
Exactly. Fantastic. Thank you. So yes, this is really interesting because when we are training the model, sometimes after we train the model, well, when we perform inference, the conditions over which we perform inference may be similar or different to the conditions over which we are training the model. So this is a very simple schematic of like a model being trained where we have like a data set where typically the data is available beforehand. We extract from that data set an input that we want to fill a model, and also the target, which is what we want the model to generate in presence of that input. The model generates an output, and then we compare the target with the output through a loss function. Well, yes, during training, data is typically available beforehand. So during inference, if we have the whole audio available, let's just say that we have the whole audio in the hard disk, as I was saying before, well, we can keep the same strategy. We take the audio and we run the model once across the audio, the input, and we get the results. And this is a really common non-continuous way of processing audio. But Jatin, if you want to continue.
Yeah, so the problem is that when we need to do real-time inference, we're going to have to keep up with this incoming data, and we're going to need to keep giving results back to the system that we're working with. And so in a more kind of specific way, often what this means is that we need to keep around some context from previous calls to make sure that we can maintain continuity. So if you think about like how you might kind of naively do things, or similar to what Fran was saying about the training process, is that you'll have some input and you'll just put it all through your network and you'll get some output. But if you have a situation where you keep getting new input, then maybe that input just becomes a longer and longer buffer every time, and so your training starts from scratch every time and might take quite a while. So another way that we can think about this is this idea of a streaming implementation, where we only need to process the new samples as they're coming in, and then for that to work, we need to keep around some state or some context from previous inference runs, so that instead of starting from scratch, the model can start from wherever it left off at the end of the previous call and keep moving forward from there. And so for the specific case that we're talking about here, that's mostly what we're going to want to do. And so in order to do this, in order to kind of do this streaming implementation, we're going to do it a little bit similar to how we would do most other real-time DSP algorithms. So we're going to have a block-based processing kind of framework. So usually the way this works is that you have some host system, maybe it's your audio driver, or if you're in like an audio plugin, the callback is coming from your DAW. And the host system will give you your data in chunks, and it'll call some function that gives you new data, and you're supposed to give it back the process data. And so this ends up working out pretty nicely because the blocks are all going to be sequential in time. And so you can just take each block as it comes in and process it. But if you want to have any kind of like future sight, you're going to need to add some latency kind of manually. And we'll talk about this a little bit later on as well. It also means that you need to manage what state needs to be persisted between these callbacks and kind of manage that yourself as well. And then another kind of detail that you might need to think about, depending on your specific network that you're implementing, is that you may not be guaranteed that all the blocks will be the same size. This is especially true in audio plugins. But yeah, it depends on what your host system can guarantee. So in order for the streaming to work, we're going to kind of think about it in two ways. So first, coming at it from a block-based processing perspective, we're going to think about how do you design your neural network architecture so that this block-based processing will be able to work at all. And then once you have that, how do you set up your inferencing so that it can be real-time safe and work in this streaming fashion? And kind of as a more general thing, we're going to try to think about things with a little bit of a different paradigm and thinking about the way that we understand our forward paths through our network a little bit differently. And yeah, this is something that Fran's going to pick up from here and talk about the training process.
Well, yes. So what we want to argue here is that for streaming models, for models that are suitable for running real time and thus keep a state of the previous calls, we are going to have to change a bit the paradigm from that we inherit when we are used to work with training models and with non-continuous processing. Because again, if you have the audio beforehand, you can just call the model once. But if you want to process audio as it is coming, because you are processing it in real time with a cap in latency and jitter, well, we are going to have to call this model several times per second to keep up with the incoming information, and thus we need a change of paradigm. So what I'm going to share right now here is the main rule of streaming architectures. This is the way we call it. And again, this works exactly in the same way when we consider that we have like a DSP algorithm running in real time. So let's just think that we have our system, and our system we process audio in chunks of only 4 samples, right? Because it's easy to depict here in the presentation. So we have an input, it is 4 samples, right? At t equals 4, we have the inputs x0 from x3, right? Well, we take this block of inputs, we run them, we perform inference through our model, and we have a set of outputs. Let's just say that our model is, I don't know, emulating a compressor, so we feed 4 samples of input, and we have 4 samples of output, right? Y0 from 0 to 3. Well, that makes total sense, right? Then at t equals 8, we're going to have a new block of 4 samples. We're going to feed the model those samples, and we're going to get 4 samples as an output. And then at t equals 12, we have the same situation. 4 new samples, we feed the model, we generate 4 samples in the output. So what is the main rule of streaming architectures, of real-time architectures? Don't break the time-space continuum. This is a little bit exaggerated, but what we want to say here is that for each block that we generate of an output, we have to have a corresponding input block. So there has to be a one-to-one equivalence between the output block and the input block. So if I have an output block of 4 samples, that means that I have to have an input block of 4 samples here, in the case of this example. There has to be a correspondence between inputs and outputs that should not be broken. Fantastic. So we're going to dive into a little bit 2 different audio models for cloning effects. So these models are useful for emulating compressors, distortions, different types of audio effects. We're going to start by looking at an RNN-based audio effect modeling that we have here. It consists of an input, which we can call X. We have an RNN layer that we're going to talk about a little bit. Then we have a norm layer and a linear layer, and then the output. Well, this RNN layer encompasses the dynamic behavior of the effect that we want to model and receives single samples as an input and creates a vector state as an output, which is a model which models the current and the previous samples that the recurrent layer has seen. So that's why we have this model, this RNN layer, has as an input the sample input, but also the previous state. That is the way in which it models the previous samples. It has the xn, which is the current input, and h of n minus 1, which is the previous state vector. And it generates an hn, which is the current state vector. So the whole idea is that it keeps the dynamic behavior of the system because it stores the output, and that output is used on the next sample. So the initial state, which is at n equals 0, the first sample that the RNN receives has x0, but the h is initialized as all zeros, this vector of previous state. And of course, this is the dynamic behavior of the system. Then we have a normalization, which is a really simple scalar multiplication and a bias and an addition of the state. And then we have a linear layer, which is just performs matrix multiplication of this normalized state into project this into the yn output, which is a single sample, and that's the sample that gets output by the system. So when we are running this model in streaming, how can we support this model? Like, how can we support inference when we need this model to be called over and over again with new samples? Well, the modification that we need to do for streaming is really simple. We just need to store the state output so that it is available as the previous output, as the previous state for the next call. We need to store this value so that next time we have another block of samples, we can provide this hn in the input of the previous state. So that's easy enough. It's pretty simple. It's a very simple modification that we need to do. But usually these audio effects are also modeled with convolutional networks. And in this case, we have a convolutional neural network effect modeling here that is composed of like a set of convolutional layers with a nonlinear activation and then a mix that we're going to see in a second. So this nonlinear activation is a very simple model, doesn't require any modification for streaming, and it is an element-wise operation. That's great. Then we have the mix, which pretty much is a matrix multiplication that takes the intermediate outputs of these convolutional blocks that we have here. Each convolutional block is, again, one convolution layer and one nonlinear activation layer. It takes all these skip connection, these intermediate states or outputs of these blocks and projects them back into a single sample. And then we have the convolutional layer. This convolutional layer, again, is the dynamic behavior of the model, represents the dynamic behavior of the model, and the whole idea is that here, instead of using a recurrent layer, we stack different, like an amount of convolutional layers between the input and the output, and by doing that, we not only model the dynamic behavior, but stacking more layers actually allows us to increase the equivalent impulse response of the system that we want to model. So this is great. And then again, like if we want to take a look at this model, the linear layer, this matrix multiplication called mix here, does not aggregate samples through time. It just projects the current intermediate states or outputs into a single output. So that is ready for being implemented in a streaming fashion. The same as this simple sigma function, which is like the nonlinear activation, which is an element-wise operation. So what we need to look into more detail is the convolutional layer and trying to understand how can we implement this in a streaming fashion and what kind of modifications do we need to do. Because again, the convolutional layer is the layer that actually aggregates samples through time. So let's start with a very simple example here. We have, again, a convolutional layer can be seen, and it is the equivalent of an FIR filter, particularly in this very simple example where we have like an audio channel, which is like a one-channel input, and we have a one-channel output, and we have a convolutional layer that has a kernel size of 3. That means like the FIR filter of this convolutional layer has a length of 3. That's the impulse response of this FIR filter is n equals 3. So we have an input that is xn, we have a learned set of weights, and we have an output, right? So we can depict the input as like, for instance, a collection of 5 samples, and we have this kernel size of 3, and we slide the kernel across the input to perform the convolution, right? The first stage is like we perform the inner product between these 3 values and the kernel, and we generate y0. Then we slide the kernel across the input, we perform again like inner product, and we generate the second output, and then we do the same and we generate the third output, and wait, this is a little bit weird. we have broken the time-space continuum. What is happening here? We had 5 inputs, 5 time samples, right? 5 audio samples as an input, and we generate 3 audio samples as an output. So yeah, there's something that we don't have to do. It's not as exaggerated as this problem where like we are not generating a black hole inside the computer, but this is pretty bad. This is pretty bad because this system is not ready for being implemented in a real-time fashion. So let's take a look at what can we do about it. Let's try to adapt this convolutional layer for streaming so that we don't break the time-space continuum that we were talking about. So let's go back to basics here. When we consider that we have an FIR filter running in a DSP real-time system, we can consider a streaming convolution again as an FIR filter that runs in real time. And what we have is like, we have an input buffer. Every time we receive one input, we store it in a buffer, and that buffer allows us to compute the inner product to generate the output. The buffer length in this case is similar to the kernel size, that is the length of the filter, in this case 3. So if we take a look at the initial buffer state that we have for an FIR filter of size 3, the initial buffer state when we receive the first sample looks something like this. We have all zeros, and then we have the first audio sample there. And that's great because we can compute convolution, right, and get an output, y0. And we can continue this with more samples. So continuing the example here, we have the 5 total samples, and we slide the kernel across the input, or we could say that we slide the input through the buffer is equivalent. So what we do is like we compute the next sample, the next output, and so on and so on and so on, and hey, look at that. Out of the sudden we have 5 inputs and we have 5 outputs. So this is starting to look more sane. This is starting to look at something that we can actually implement in real time. That means that when we want to implement this, in order to keep the input and output sizes consistent, we need to add extra values to the input when we train the system so that then we can deploy it in real time properly. We add these extra values to the input when we're training in order to mimic the streaming case that the system will see when it's running real time. So this process of adding additional values is called padding, and we use padding during training, again, to mimic the real-time buffering strategy that we're going to do for each of the layers, the convolutional layers that we want to implement. So we have coaxial padding, which is where we have an initial kernel input, and we add zeros to the left. And this is great because this type of approach only needs x0 to produce y0, right? Like the initial kernel input sees this kind of information, so y0 will depend of like 2 zeros and x0. And this is great because it will limit the amount of latency that we need to wait until performing. We're going to see in a second. But this is great because this is coaxial, which means that only needs one input to produce one output, one time step. And then we have also symmetric padding, right? In this case, if we add 1 0 to the left, 1 0 to the right, well, the first output, which is y0, will depend on x0 and x1. That means that in a real-time scenario, we need to wait to get x1. It's not enough to compute it with x0 only. We need to wait to get x1 before computing the first output of the model. And that is called, in real-time jargon, is called look ahead. We need to wait for x1 in order to produce y0. That's why when we deploy these models for training, when we design them for training, if we add right padding, that means that we are going to have to add a delay line in that layer in order to wait for the appropriate amount of samples that we need for generating the first input. And this is great because this allows us to trade off delay versus accuracy of the model. The model usually performs better when it has a look ahead, of course, but we're trading off this thing. And then we have left padding, which is the rest of the padding that we need to add up to the buffer length that we are going to use. In the case of a kernel size of 3, as we said, we need 2 padding time steps that we need to add. We can add it in a coaxial way, we can add it in a symmetric way. That's good. So, in summary, the types of modifications that we need to add for streaming. for convolutional models, during training we need to add padding to keep the input and output sizes consistent. And for streaming, what we need to do is we need to store the previous inputs in a buffer. Of course, during streaming is exactly the same as we would perform streaming with an FIR filter. We need to keep the inputs that we are receiving in a buffer in order to have them ready to, for computation every time we receive new samples. And if we are doing write padding, we need to add delay lines accordingly. For an RNN layer is much more simpler. What we need to do for streaming is just to store the previous output of each of the RNN layers in order to have that previous state ready for whenever we have new samples. And for linear layers, normalization layers, activation functions, we usually don't need any change because they don't aggregate samples through time, so we are good there. And for skip connections, well, only for when we deploy them for streaming, we may need to add delay lines if we are skipping a layer that had write padding. So if we have a layer that has a delay line, we need to add also the delay line to the skip connection. Well, great. So to wrap up this section of concepts and modifications, real-time model for neural audio need to be causal. That means that they have to have limited or zero look ahead. Therefore, we need to apply padding in convolutional layers, or just use the standard RNN layers, which are fully causal. They need to be stateful. That means we need to store the context, whether we store the outputs of the RNN layer or the inputs on a buffer in the CNN layers. We need to have them made stateful to be able to run in a streaming fashion, so that we store the context across every time we call the model, because remember, we are going to call the model several times per second, so we need to store the context of the previous calls. That's why we need to modify the operation of several layers. And also, real-time model for neural audio should be hard real-time, in order to guarantee latency and jitter margins. So inherently, the model it can be real-time safe, but it just depends on the type of compute environment on which we're running this model. And so we need to run this model in a real-time safe environment, which we're going to see in a second. And finally, we would like these models to be as efficient as possible in order to run on CPU and mobile and embedded systems for the typical use cases that we have. We're trying to perform to clone a compressor, for instance, so we don't have enough time to send a bunch of samples to a GPU, perform the calculation there, and obtain the result. So in these cases, we need to have models that are really efficient in order to be able to run on CPU or mobile or embedded systems. So I wonder, what kind of framework do we have available to deploy models with all these requirements?
Yeah, it's a good question. So I guess the answer is this framework that I've been working on with a few collaborators for a while now, called RTNeural. And this came out of kind of the question that Fran was asking about, like, oh, if we want to be able to run our inference on our CPU in a way that's real-time safe, what are some available options? And at the time, there weren't that many available, so that's why I started writing RTNeural. And so the basic idea is that we have our neural network and we do all our training process, and then if we're going to be doing inference in kind of a different framework or a different language or any different way than how we did it during training, then we need to figure out a way to save our model weights so that then we can move over to our training environment and reuse those weights in the training environment. And so for the process of saving the weights, we're going to need some way to export them, and there's a bunch of different formats that I played around with here. I think kind of the default thing that I mostly use is JSON, which has some trade-offs. There's some good things and bad things about JSON. You could do, pretty much any format. Any other text-based format or binary format should work fine. Then for actually the part of doing inference, you want to make sure that you're working in a real-time safe language, and then you want to make sure that within that language, you're using language features and writing your code in a way that will be real-time safe, at least for the part of the the part of your code that's actually doing the inference. So when we say that we want things to be real-time safe, really what we mean is that we don't want to be missing our real-time deadline. So there's this great article by Ross Benzina called Real-Time Waits for Nothing, where he describes this in a bit more detail. But the basic idea, the Cliff Notes version, is that when we're writing audio code, we have some deadline, and we need to finish processing our audio before that deadline. And if we don't, we're going to get some kind of glitch that probably we don't want. It's not going to sound very good. And so the general rule of thumb is that if you don't know how long something's going to take, if something has what you might call an unbounded execution time, then you shouldn't do it. And usually where this comes up is when you have to synchronize with some non-real-time system. So for example, if you need to synchronize with some other thread, you might typically want to use like a lock or a mutex or something like that. That's usually a bad idea in your real-time code because of a problem called priority inversion, where now your OS thread scheduler is trying really hard to get your real-time thread to make progress, but your real-time thread is waiting on some other thread that has a lower priority, and now you're potentially waiting a very long time. This also tends to come up quite a bit whenever you're dealing with some kind of shared resources. So a very common example is memory allocation, but this also shows up when you're doing logging or syscalls or things like that. So those are just some things to watch out for if you're trying to write code that needs to be real-time safe. So with RTNeural, the idea is that we wanted it to be kind of a streaming by default inferencing engine. So the natural way that you write your code should be in this sort of streaming format. And I've mostly been using it for like audio processing things. I've heard of some other people looking at using it for like medical devices and things like that, but I don't really know how well suited it is for those applications. But the general idea is that you want to have kind of these stateful and causal layers that are guaranteed to be real-time safe, and you can just kind of integrate them into your C or C++ application kind of in this streaming fashion that we mentioned. We also try to get as good performance as we can, and through part of that, we have kind of these 3 different computational backends that you can try to, see which combinations of backends work the best on which devices and things like that. And then there's also a couple different modes of optimization or of operation. So there's a static mode where the neural architecture is defined at compile time and it can't really be changed. Or there's a dynamic mode where you can kind of build your model up at runtime and figure it out that way. We try to make both modes very fast, but in general, the static mode will be more optimal just because the compiler can kind of see through what you're trying to do and optimize a lot of the steps. So the general process is that you declare the layers that you're going to use, and then you load the weights from your trained model into those layers. And then you have to define the compute graph in some way. If you have a sequential model where it's just like one layer after the other, then we have some kind of utilities in the library that make that a lot easier. If you have a more complicated architecture, then you have to define a few more things for yourself, but it can work really well. We have a whole bunch of contributors who have done some really great work, so I've been kind of maintaining the project, but all of these people have contributed really valuable parts to the project. And I'll give a special shout out to, I think it's pronounced Matthijs on the far right there, who designed this logo that we've been showing all over the place in these slides. Yeah, he did a really good job with that. Yeah, so just to kind of give you a flavor for what this kind of code will look like, let's imagine that we're training some model in PyTorch, and we have a very simple model here. We construct the model, and we can put some data through the model and do training and whatnot. And then at the very end, when we're done training or done doing whatever we need to do, we want to export the model weights. And so here we have a little example of exporting the weights as a JSON file. On the C++ side, we're going to kind of do the same thing in a slightly different order. So first, we're going to define our model, and you'll see that it's defined as a type. So the idea here is that the actual kind of data flow through the model is encoded in the type at compile time. Then we'll construct the model, and then now we're going to load the weights from the JSON file. So we have to kind of load the JSON file into this C++ JSON representation. And then from there, we can actually load the weights directly into the layers. And then finally, at the bottom there, we can actually call this forward function on our model and put some data through it. And that's kind of the idea. So we put together a little example to show you all kind of the end-to-end process of going from training a network to implementing it in C++ and getting some output from it. So we'll go over now to this Python notebook that I guess people can follow along.
Yes.
Should we put it in the like in the comments or whatever of the?
Yes, the information you have the link in the description of this video. There's a link that takes you right there to a very short website that has some further information about latency and about this example that we're gonna run, and also has the link to the notebook. And yeah, I think there are some examples also for RTNeural. There are some interesting links. And yes, we're going to run and go to the notebook right now. So let's move here. Let's go to the notebook. Okay. Fantastic. Oh, almost. I think I lost you there. Okay. Let's see. Yes. There you are. Great. Okay. So let's go through the notebook. So in this notebook, what we're going to do is we're going to train and deploy a streaming neural audio model based on convolutions from scratch. The whole idea here is that we have some training data, which is actually from a fast pedal that Jatin built a few years ago, so that's great. We have even made our own training data, and we're going to download this data. We're going to declare some important layers and blocks for this model, especially the convolutional layer with causal padding that we were explaining before. We're going to declare the model, which is a very similar model to the one that we show in the slides. We're going to take a look at that in a second. We're going to train it. We're going to analyze how it runs in PyTorch, which is the training inference that we're going to use. And finally, we're going to deploy it right there in the network, in the notebook in C++. Okay, so let's just start. Connecting now to the server here. Great. Okay, so we're going to download the audio. You can also give it a listen in a second. Right, let's take a look. This is the audio data. So this audio data is an aligned input and output that we have. Therefore, we have the input, which should be like a clean guitar and a test signal, and the output, which is the processed waveform by the pedal. What we're going to do is that we're going to use the input to feed the model and the output as the target, as to show the model what we want it to learn. So let's take a look. Let's adjust a little bit the volume first. Great, that's the input, which is at that point was like a test signal, but here we have some guitar playing too. Great, and this is the output of the model. This is the output of the, not the model, this is the output of the training data that we want, of the original pedal. Nice, and a little bit of guitar playing, distorted, fused up guitar playing. Fantastic. Okay, that's our training data, and it's great. Only with 30 seconds of data is going to be more than enough. So let's take a look now at the layers that we're going to use for the model. Again, we're going to use the causal convolutional layer, which is a layer that has some padding added to the left of the input. So when we train, every time we're going to feed this model with new data, we add some trailing zeros, only during training, right? Again, we are going to, these are two variants, which are the variants that we were talking about, the causal variant and the symmetric variant, the causal padding and the symmetric padding, and we're going to take a look at that right now. So we are going to declare this layer, which is a very simple module within PyTorch that we declare that is called causal conv, and the only thing it does is like it runs a convolutional layer, but before calling this layer, it adds some trailing zeros here. The amount of trailing zeros that it adds depends of, like in this case, depends of only two parameters of the layer, which is the kernel size that we were saying before, and also the dilation that we're going to show in a minute. But we declare this layer here, this layer is ready, and we can actually test it. So we can test, we have this very simple example, which is an example over which we run 5 samples of audio, 5 random samples of audio over a single convolutional layer. And we can see that if we run the convolution without any padding, as we have seen here, we, as I showed in the slides, we see that we are breaking this input and output correspondence. Let's take a look. So we are declaring a convolution layer that has one input as one channel as an input, and it generates 16 channels of audio, of convoluted audio as an output, of filter audio as an output. And what we can see is that the standard convolution layer here generates 16 channels, as we said before, makes sense, of 3 samples each. So it breaks down these correspondence that we were talking about. But for instance, if we use center padding, which is a standard padding configuration option in the original convolutional layer in PyTorch, it actually works. It gives us 5 samples. From 5 samples of input, it gives us 5 samples of output, which makes sense. But we need to be very careful here, because this padding that looks padding equals 1 is symmetric padding. And again, if we test our own causal convolution, also gives us 5 samples each from an input of 5 samples. So this makes sense, and it doesn't break the correspondence. Fantastic. So this we have run already. Well, we're going to train a model, this particular model in PyTorch. Jatin, if you want to say a few words about it.
Yeah, definitely. So the general idea is that it's going to be kind of like the convolution stack network that we saw in the slides earlier. So basically, we have convolution layers. Each convolution has an activation layer after it, and then the dilations of the convolutions are going to be growing in powers of 2 as you go up. And then I guess kind of the difference between this model and the model that we saw in the slides is that instead of doing skip connections, we're just going to keep everything sequential and put it all together at the end.
Yes, fantastic. And what about the dilations?
Oh yeah, so the dilations, the idea with the dilations is that by growing them over time, you're kind of expanding the amount of time that the convolution is operating over. So you can think of it similar to like an impulse response. Like with an impulse response, you have kind of a time, like a length of time that the impulse response is going to operate over. That's defined by the length of the impulse response. So it's going to be similar with convolutions, that kind of the, I think it's the kernel size times the dilation is basically the number of samples that it's going to be able to operate over.
Fantastic. So let's take a look at the model now. It's exactly as you were saying. Yeah, if you want to say something else.
That's all right. Yeah, I think it's mostly self-explanatory there, just kind of going through the code with the causal convolutions kind of, yeah, in a stack there. And then you can see there's that one line there where we define the dilations as like a power of 2 sequence, that kind of thing.
Exactly. Perfect. Okay. So we have this stack of layers, and then when we call the model in the forward process, the only thing that we do is like we pass them through the different layers, and we generate the output. So this is what we call also like a sequential model, right? It's a model over which we have like a stack of layers, and each each layer receives the input from the previous layer as an output. That means, let me say it again, like there's a succession of layers and each layer receives as an input the output of the previous layer, and like that it goes, and there are no skip connections, nothing like that. Said it in a hopefully a little bit more clearer way. So okay, let's declare this model, let's run this model and let's have it declared. Great. And we can test this model too, right? We can test this model and try to check the sanity of the inputs and outputs. And what we should see if we run this is like, if I feed this model a random input, right, of like 44100 samples of audio, well, the output is going to be also the same amount, 44100. That means that we are not breaking this correspondence, right? We have the same amount of outputs as inputs the model has seen. So this looks good, and we know by design it has coaxial padding, so this is pretty much like ready to deploy in RTNeural after we train it, of course. So if whoever wants to access this notebook later and take a look at the loss functions and the way we train this model, that's all right. And we're going to just run this. How can I run? Ah, there we go. We're going to run this just to concentrate more on the inference process that we are going to have. And then we can call the training system and train it for a few epochs. Here we go. See if it is training. Yes, apparently it's starting. Nice, it's started to train. And pretty much what we're doing here, as the model is training, takes 3 minutes. We can say a few things about this. Well, we declared this model, as we said before, with 6 layers, 6 intermediate layers. Each layer has inside like 16 channels. So it's always in exchanging these 16 channels of audio. And the kernel size of each of these layers is 3, but of course some of the layers have dilation, which means that they have an increased receptive field, but only with 3 values, right? All the other values that are dilated are zeros. That's the way dilation works. And yeah, we're training with a specific optimizer. We are using the data as we saw before, and as we see, the loss has started to decrease. And in a few epochs, we're going to be ready to proceed, and we're going to have the model trained, and we can take a look at how is it performing, right? So first of all, after it gets trained here, it will stop in a minute. We're going to use this model for what we call as non-continuous inference. So we have the model, it's trained already. And what we're going to do is like we're going to have a chunk of audio that it is already available in the disk, and we're going to call the model only once with all this chunk of audio, and we're going to receive as a result a processed chunk of audio, but only by calling this model once, which is the example that I was giving before, right? Hey, there we go, it finished. So the example that I was giving before, which is the non-real-time case, is that I have my audio already available. I don't need to call the model several times to keep up with incoming data because the data is all already there. I call the model only once with the input and I receive the output. So let's just run this from the validation set. We're going to run like a chunk of audio that is already available, and we're going to call the model only once directly from PyTorch, right? We are not doing any RTNeural or any C++. We run it only once, and what we can see here is that the model seems to work pretty well, because we have the input audio, which is this blue signal here. We have the target audio, which is the audio that we wanted the model to learn, which is the orange one. And then we have in this dashed green line, we have the predicted audio. And as we see, yes, maybe in the first samples, it's just starting up, but after like just a few samples, the model starts to behave really similarly to the target. So much that it's going to sound pretty similar. So this is what happens when we run the model. We call it only once in 20 milliseconds of data. It could have been 20 seconds of data, and it shows a response pretty similar to the target, which means that the model is trained. And we can run it directly on PyTorch when we have the audio beforehand available. Fantastic. So let's see what happens now And I don't know, Jatin, if you want to talk about this one. Let's see what happens now when we have the model and we run it only once with the whole audio. Again, this is the same result that we're going to get. We call the model only once here with the full data, and we have the output here, and we can actually listen how it is sounding. So let me first adjust the volume here. This is the input. The target, which is what we wanted the model to learn, is here. And the output, what the model actually learned, is this. Which sounds pretty similar, right? Jatin, do you agree?
Yeah.
Okay, let's move on. Fantastic. Okay, so let's try to run this model again. Let's try to run this model again in PyTorch. Do you want to say this one?
Sure, yeah. So basically what we're seeing here is if we try to kind of chop up the inferencing into these blocks as we go through and process each block separately. So you can imagine this is like if we're in kind of a plugin or like a callback scenario where each callback we get a new chunk of audio, and we're just going to process that directly with the same PyTorch model that we saw. And yeah, let's see what it gives us here. Oh, I think
too long, right? It worked. So pretty much what we're doing here is exactly what you were saying, right? We're chopping up the input audio in blocks of 16 samples. So we're actually simulating a real-time use case where we need to call this model several times per second every time we have a new block of samples. In this case, we're simulating it with 16 samples, right? And we're running it directly on PyTorch. So what happens here?
Oh, I think what I'm seeing is a little bit behind where you are.
Oh, really? Okay.
Yeah. Oh, okay. There it is. Yeah. Yeah. So what we're seeing there is, well, first of all, it's obviously not as accurate as the last plot that we looked at. But kind of more specifically, what we're seeing is that like there's these points where it seems like the model is doing something, and then all of a sudden it just kind of restarts at zero, and you get kind of these chops. And so that's basically what's happening whenever you reach the end of your block, and what we've been calling the context kind of resets, and then yeah, everything gets messed up.
Exactly, it looks pretty choppy, and it is not doing at all what it is supposed to do, right? Because it's supposed to give us a waveform that is really similar to the orange one, as we saw before. Before we had this that was really similar to the orange one, but now it's giving up like a pretty choppy, broken up audio. I don't think we have put something to listen to this, but I wouldn't like to listen to this. But you know, if anyone that takes a look at this wants to listen to it, well, why not? Yeah, go ahead and you can download this notebook and edit it however you please. Anyways,
yeah, we can turn your volume down though. It's probably going to sound a little.
No, but actually we don't have it. We don't need to listen it because actually we don't have it here. So easier for our ears. Okay.
Yeah.
So fantastic. We can actually move on to running the streaming implementation with RTNeural, right?
Perfect. Yeah. Yeah, so basically what we're seeing here is similar code to what we saw in the slides, where we just want to export the weights of the model. And again, we're going to use this kind of JSON format here. So that's yeah, not too complicated. And we can actually see here, it's nice, it prints out a little kind of not exactly a diagram, but kind of a text representation of the model architecture, which is kind of nice.
Fantastic.
Yeah, then we can actually clone RTNeural and get that ready for working. And then we have the actual C++ code down here a little bit further.
Fantastic. So real-time inference. Fantastic. Yes.
Oh yeah, there it is.
We can declare the leaky ReLU here.
Yeah, there's some like implementation details that yeah, we don't need to worry about right now.
Exactly, and we have the actual inference code in RTNeural here.
Yep. Yeah, so here's the kind of useful stuff. So again, it starts out similar to what we saw on the slides, where we take kind of this JSON file and just load it in to our C++ program. And then again, we have this sort of type declaration that's going to declare our model architecture as a type. So again, this is something that is all happening at compile time, and it's all something that compiler can kind of see through and optimize through. You might look at it and think that maybe some of this should be done with loops, and in a sense, you're correct. Like there is some very repeated code here, but I didn't want to use like I don't know, doing compile time loops in C++ is kind of ugly, so I didn't want to do it here just to save you the it would be a lot harder to read if I had done it that way. So this is a little better, even though it looks like very repeated code. And then similarly, we can go through and load the model weights, again, just going layer by layer and taking the layer weights that we need from the JSON file.
Yes,
and then finally at the end here, we can actually go through and process the audio. And we're kind of, there's a little bit of extra code here for timing how long it takes, but basically we're just gonna go through our audio buffer sample by sample and just process each sample as we get it. And then print that to the output. And then, yeah, we're gonna compare the output of the C++ program to the what we got out of the Python model, which will be an interesting comparison here.
Fantastic. And like just to highlight a crucial difference here in this code with respect to the PyTorch code. What we have here is that we are calling the model every time we have a new sample, right? Which is a stark difference in comparison with the other use case that we have, where we would call the model only once with the whole audio. In this case, we call the model every time we have a sample. So if we have 1 second of audio, well, we call the model, let's just say 44,100 times, which is really interesting because the model is storing the context every time it gets called. After it gets called, the model stores the context of the previous run, so we can actually call it using one sample, or using 2, or using 16, or using 128, however we want. But in this case, we're going to see that hopefully it will work. So what we're going to do now is, like, we have written these two files into like the notebook. We can run the compiler now. There you go. And Jatin, you can tell us what happens here when we run the...
Yeah, so now we're going to actually run the models, and so we can see here it's going to tell us how much time it took to actually do the inference. And so we can see here that we're getting around 25 to 30x real time, which is pretty good. There might even be ways we could improve that further, but yeah, for most use cases, that should be acceptable. The way to think about that is that you could essentially run like 30 instances of the plugin in series on one thread without missing your real-time deadline. There's a little bit of variance in there, so maybe like 29. But yeah, then we can go through and plot the output against our original data here.
Plotting it right now.
Yeah, it'll look pretty close to what we got from the Python model. And if you want, we can actually check directly against the output of the Python model and see how close it is.
Really close.
Yeah, so I mean, there's a little bit of error, but it's probably around what you would expect from just like floating point arithmetic, kind of that kind of uncertainty. So yeah, that should be acceptable for most like audio use cases. And then again, we can actually listen to our output here if you want to play those.
Yes, fantastic. I can. Let me adjust the volume a little bit. So we have again our input here. We have the target, which is what we wanted the model to learn. We have the output of the PyTorch model, I believe. Yes, the PyTorch model that ran the whole input using one single call. And we have the inference done by RTNeural. And yes, it does sound the same. Fantastic. So yes, that's been the presentation. No, we actually have a little bit more, right? Yes, we have a few closing remarks now that we can give to for whoever is online and for whoever that happens to take a look at this stream later. So let's go back to the presentation actually. Let me go back. There we go. So we are back into the presentation now, and what we're going to do now is we're going to try and disambiguate a few concepts that are usually being conflated from time to time when I hear people talking about latency and real time and streaming inference. So we just want to leave these concepts as clear as possible, let's just say, and let's take a look. So what we did here is some kind of like Russian roulette where we mix and match some concepts and we try them to compare with the concept of real time. So I shall start. Let's do the first one here. So we need to compare the concept of efficiency with the concept of real time. Well, an efficient algorithm is an algorithm that can potentially perform better than other, can do the same task better than another that we have as a reference in terms of whether it's like computing time or energy consumption, again, or latency. So the whole idea here is that we need efficient algorithms. We prefer efficient algorithms to be run in real time because when we run things in real time, when we run algorithms in real time, we have an execution time bound. So yes, it's not a hard requirement that an algorithm must be efficient in order to be able to run them in real time. But if we are talking about running algorithms in real time for audio processing, we usually want to keep the latency short. We need to run them in small block sizes. So we prefer having efficient algorithms so that we can respect the deadlines of latency and jitter that we impose in the system when we run them in real time. So Jatin, you want to do the next one?
Let's do it.
Causality.
Yes, causality. So I guess the way I would think of it is that kind of causality is sort of like an algorithmic precondition for real time. So if you want to be able to run something in real time, you first need to make sure that it works in a way that's causal, and then you can worry about whether or not you can implement it in real time. Just from like an algorithmic perspective, I guess like it being causal means that you only need your previous data and you don't need any kind of future sight or knowledge of data that you haven't seen yet. And so if you want to be able to implement something in real time, then you're kind of going to need that anyway. So if you're able to make your algorithm causal, that's like the first step, and then all that extra real-time stuff can come after.
Exactly. And if you're going to add look ahead, well, it has to have finite look ahead, right?
Exactly.
Exactly. Let's do another one. My turn. I'm scared. Latency. Okay, so this one was an easy one. So real time versus latency. When we decide to run an algorithm in real time, we need to put usually a cap in the amount of latency and jitter, that is the variation of that latency that the results should present. So a result that comes after the deadline that we set, it is an incorrect result, even if numerically is correct. That is the cap and the boundary that we put for real-time algorithms. So yes, if we say that we need algorithms that have bounded latency so that we can run them in real time. So if an algorithm has a natural latency of 1 second, well, that's good enough as long as we have a real-time system that has those requirements of latency. Shorter latency that it can run in with a bounded latency of 1 second and not more than that. That's the idea. So it's like as long as we bound the latency, we can use any algorithm that has that lies within those latency boundaries. Hey, it wasn't that as easy as I thought it was going to be. Okay, let's do another one.
Stateful. Okay. Yeah. So the way I would think about stateful is that, like, if you have a network that is stateful, then you need to kind of make sure you're handling that state properly to be able to implement it in real time. So if your network has some state and you want it to be implemented kind of in this streaming fashion that we've been talking about, then you need to make sure that, like, between calls to your network or between calls to your program in general, that you're keeping that state alive and persistent and not overwriting it or zeroing it or things like that. And then if you're able to do that, then you can make it work in real time.
Fantastic. And then finally is streaming. Okay. So a streaming algorithm, let's just remember that a streaming algorithm is that algorithm that can be called several times per second and keep context, because it is stateful, it can keep context of the previous calls. Therefore, it doesn't chop up the audio, we could say, or it doesn't generate a broken output, because it remembers, it keeps a state that remembers the previous audio inputs that it had. When we execute as a real-time system, we put this cap in latency and jitter, which means that we need to run usually this algorithm several times per second in order to keep up with incoming data. If we don't keep up with incoming data, we are going to break the deadlines that we set, and therefore the algorithm is not going to run in real time. Therefore, to keep up with the deadlines that we set in real time, we need streaming algorithms that can keep context and can be called lots of times per second, ideally, in order to keep up with incoming data and not break the real-time deadlines that we have. Anything more?
Yeah.
Okay, no, that is. So, exactly. Some final remarks then. Like for many situations, implementing audio processing neural nets in real time is surprisingly straightforward. If you design it well in Python, in PyTorch, then it may be really easy to deploy them in C++. And we saw the example from the notebook. But again, the real-time implementation starts in Python or PyTorch. So it is not a question of, designing and training the model and then remembering, oh, it would be nice if I run this in real time, and then you face that the model is not compatible with the real-time use case. So that's why we need to use a suitable architecture. And again, in terms of what it is easier to deploy, in RTNeural, causal models with no look ahead are usually the simplest to deploy because RTNeural actually provides layers that work in that fashion. So remember something important, real-time, the fact that it's real-time doesn't guarantee low latency, so you need to consider the inherent latency of these algorithms, if they have, before running them in real time. The fact that you run something in real time doesn't guarantee that it's going to run with low latency. Real time, again, does not guarantee that we have a low CPU use. It just tells us that we have put deadlines in terms of like the latency and jitter, but maybe the algorithm is really expensive to run and you cannot run it in real time. So finally, always check for correctness and efficiency when you have a deployed RTNeural model, because again, like it is a question of designing what we're going to do, have a suitable architecture deployed in PyTorch available, and something that we can then translate as simple as possible in RTNeural. And after you do that, then it's important to check that the RTNeural model is actually running as it is intended. So yes, that's pretty much it. Thank you so much for staying connected. The people that is right now looking at this live stream. And yeah, it's really been a pleasure. Let's go back here. Opa. Let me find you, Jatin. Where are you? There you are. Great. Now you are on the stream again. And yeah, no, thank you so much, Jatin. Again, like I dragged you into this for the presentation a few months ago, actually, and it's been great doing it with you, and I actually learned a lot while doing it, and yes, it's been great. Thank you so much. And
of course, yeah, had a lot of fun.
Yeah, fantastic. So yeah, and if anyone has any questions right now, We have 7 people actually taking a look at this. So that means that 7 people, you know, have to endure through this stream. That's fantastic. Thank you so much for your attention. If you have any questions, just feel free to put them in the chat. And if you don't have any questions, that's okay. And if you happen to have any questions at a later point, you can always come back here to the stream and yes, and take a look at that. And I will be happy to answer any questions that you may have at a later date. It will be here.
Yeah.
So yes, thank you so much, Jatin, again, and yeah, I hope to see you really soon. Maybe you can come back and present something about your PhD that you're starting right now. And yeah, I wish you the best of luck for this new journey that you are doing right now.
Definitely, yeah, that'd be fun.
Okay, fantastic. Well, that's it then, and thank you so much for watching. And yes, hope to see you soon, everyone. Domenico is writing. Love you too, Domenico. Take care. And yes, all the best. Thank you. Done.
Nice.